Question 2. In circuits, DeVita is also working on the power supply for the X-ray tube. The diagram below shows part of the circuit that DeVita is testing. The voltmeter reads 18 volts. There's 18 volts across the 6 ohm resistor. Calculate the size of the current through the 6 ohm resistor. Write your answer to the correct number of significant figures. So this is just a simple calculation. I equals V over R. Just make sure that we're doing it correctly through the 6 ohm resistor. We're after the current going through that. So I equals V over R. The voltage, as we've been told, is 18 volts it reads. So remember, it's not the voltage across the whole, from here to here. It's the voltage just across the 6 ohm. 18 over the 6.0 ohms. That's two significant figures for our final answer, which is 3 amps, or 3.0 amps. B. Explain what happens to the power output of the 6 ohm resistor if the voltage across it doubles. Okay, you could be misled into thinking that from P equals I times V that if the voltage doubles, the power doubles. But that's not the case, because the current is also dependent upon the voltage. So if you double the voltage, you double the current. Okay, so that means we've got a doubling effect here and a doubling effect here. In fact, you can combine these two equations to make a power equation that's purely dependent on the voltage. And we can see that if you double the voltage, you're going to 4 times or quadruple the power. Next part, DeVita reconnects the 3 resistors as shown below. The circuit's changed so that the current through the 6 ohm resistor is now 2.0 amps. I'm going to write that on there. So it's 2.0 amps going through there. Calculate the power output of the 3 ohm resistor. So we're after the power of this, of the 3 ohm resistor. Go back to our formula, P equals I times V. We've already got R there, so we could do I squared R, or we could do V squared over R. Now, I don't know, we might be able to find the voltage. If we've got 3 amps through the 6 ohm, we can work out the voltage across that. And in fact, that's not going to be a good way. We're better off working out the current, I think. Because if we know the current through the 6 ohm, which is being given to us as 2 amps, very poorly drawn, my apologies, plus the current through the 12 ohm, because it's double the resistance, it should be half the current. So we know there's 1.0 amp through here. That means the combined current going through the 3 ohm is 3.0 amps, because we've split into 2 and then 1 down this way. Okay. So knowing the current and knowing the resistance, we can just use I squared R. So 3.0 squared times by resistance of 3.0 ohms. It's going to give us 27, and what is the unit of power? What is the unit of power? Ha. Anyway, 27 watts, two significant figures. Moving down, D, the last part. Explain what would happen to the voltage across the 3 ohm resistor. I will leave the screen on here so that we can see. Explain what would happen to the voltage across the 3 ohm resistor. So we're looking at this. Helpful to draw these little sketches on here as you go through so that you know what you're talking about. If the 12 ohm resistor is removed, but the total voltage remains the same. So that's removed, but the voltage of the supply remains the same. So whatever the voltage is across these 2 resistors remains the same. Okay, there are a couple of ways we could do this. We could actually calculate it. We could see that we're not necessarily going to remain with 2 amps going through the 6 ohm resistor, but we can, can we do a calculation for that? I don't know. We might have to do the calculations of both of the voltages across the 3 ohm from the earlier one, which using the current and the resistance, and then the voltage across the whole branch in parallel, and then if the total voltage remains the same, we can divide it up in a ratio according to those resistors, 3 to 6, from the 3 ohm to the 6 ohm. But what might be an easier approach is just to look at the current, and I'm just going to change my colour and we'll go through here. So In the first situation, we've got a parallel branch in the second part, and that means that the resistance, when you remove that, is going to be higher. So the resistance is going to be higher in that parallel branch. Okay, so let's just make a clear separation there. The resistance is going to be higher in the parallel branch. That means the resistance is going to be higher, the total resistance in the whole circuit is going to be higher. That means that the current is going to be lower in the whole circuit. So the total current is going to be lower if the resistance is higher for the same voltage. If the current is lower, that means that total current, 3 amps that's going through in the first situation, that's going to drop. So if you have a lower current going through the 3 ohm resistor, that means the voltage also has to drop. And that goes in line with what we know if we've studied voltage dividers, because the voltage divides up according to the ratio of the resistances, which is what we were looking at with this part. And because prior to removing the 12 ohm resistor, this 6 ohm part would have been a lower resistance. It might have been, say, you can do the calculation yourself, 5.5 or something like that, which means it gets less of a proportion of the voltage in that parallel section compared to here. So now that's raised to 6 ohms, increasing the total resistance across the whole circuit, decreasing the current, and if you're just sticking with the voltage ratios, lowering the voltage ratio across the 3 ohm resistor. I think you need to talk about current, and that's good to make all of those links. Don't leave anything assumed when you're answering NCEA excellence questions.